Swayam Prabha. Digital India. Educated India.
So, hello everyone, we will continue with the hook straightening process. So, in earlier section we have discussed the two types of hooks, one is leading hook, another is trailing hook, and at present session we will discuss first the hook at both sides. So, both end hook straightening process it consists of, this is formed by overlapping of leading hook and trailing hooks. So, in their body portion. So, this is the body portion and here it is a leading hook or trailing, or maybe in other direction also. So, this is the condition of the both side hooks. The straightening process is split into the 4 hook straightening, that means leading hook straightening, then rear hook or trailing hook straightening. So, this in these two stages it will be discussed. So, the abbreviations are: time taken for straightening the leading hook is T1, time taken for straightening the leading hook, trailing hook is the T2, length of the leading hook it is a L1, it will be leading hook. So, here the trail, this is actually rear hook, that is trailing hook L1, and length of the leading hook is L3. So, L2 is the length of the body part. So, L1 is the trailing hook, L2 is the body part length, and L3 is the length of the trailing hook. So, total length of the fiber will be L1 plus L2 plus L3. Okay. In this configuration, and we will discuss the straightening process separately for leading hook and for trailing hook. The process not affected by the front roller. Now, case A. So, where the hook removal takes place before it reaches the front roller. This is case A. The leading hook, that is 4 hook, straighten as the midpoint of the hook, leading hook reaches the accelerating point. So, here. So, as soon as the midpoint is reaching the accelerating point B, so it will get straightened, because we are discussing the fact that before it reaches the front roller, so straightening take place. So, R should be sufficiently high, the rear hook straightness take place as the midpoint of the body, is reaching. So, we can see here the leading hook removal takes place at point T2. and trailing hook removal will take place when as soon as it crosses point T3 before it reaches the front roller nib. That means, front roller action is not there, the body portion is moving at the speed of the front roller at T3 at this point, because the midpoint reaches the accelerating point, and the trailing hook is actually moving at the speed of the back roller. So, it gets straightened. The hooks cannot be fully straightened during the drafting. So, time for straightening will be for 4 hook, this is the time, this can be derived, we have already seen earlier also. This is the time. L n represents the L eta represents the effective length, okay. Eta is the straightening factor. Now, subtracting L3, what is L3? L3 is the length of the leading hook, accounts for the 4 hook which is not yet straightened. So, this is the straightened, this is not yet straightened. So, to consider only the portion that will undergo straightening. So, this is actually this portion will now undergo straightening, and V a plus 3 B b represent the speed at which the fiber straightening occurs. So, this relationship we have used earlier also. Now, for rear hook, so earlier it was leading hook, and now if we consider the rear hook, that is trailing hook, the time T2 will be is given by this relationship, where the L 2 eta minus 1 represents the portion of fiber that still not fully straight, and the second part V a minus V b multiplied by T 1 by 2, okay, which accounts for the effect of acceleration on the rear hook during the time it takes to straighten the leading hook. Now, as the rear hook is initially curved, the trailing hook is initially curved, it is added to the to include the part of the fiber still undergoing the straightening process. So, that is why it is there. So, output fiber straightness will be given by this equation, that eta dash output fiber straightness equal to input fiber straightness divided by E minus 1 multiplied by 3 eta minus 1 by E plus 3, this is part 1, and part 2 plus part 2 will be E minus 1 multiplied by 3 eta L minus L 3 divided by E minus 3 cube multiplied by L. So, this equation is derived, and we are not going to go for the detailed derivation. So, the output fiber straightness depends on both the drafting ratio and the initial fiber condition. So, draft ratio you can see E is the draft ratio and initial fiber condition is the eta. So, output fiber straightness is there. Now, case B is the rear hook is fully straightened during drafting. Now, here we can see this is the rear hook or trailing hook, Now, here at T2 the leading hook is reached here, and at T3 the midpoint of the body is reached. So, midpoint is body part will be moving at the speed of the front roller, but the trailing part will move at the speed of the back roller. Here the distance r is larger. So, it will get sufficient time for straightening, duration will be high. So, the rear hook will get straightened completely. So, 4 hook straighten in a similar way as this earlier case. Time for straightening for 4 hook, this is already discussed T1, and for rear hook is L1 by VA minus VB by 2, okay. And L1 is the length of rear hook and VA minus VB is the speed at which the rear hook is corrected. Now, outer fiber straightness. So, output fiber straightness is given by this relationship, where the eta represents the initial fiber straightness, and this total second part here, this is accounts for the straightening of the 4 hook, that is the straightening of the leading hook, and L1 by L is the, it accounts for straightening for the rear hook. So, when we talk about the output fiber straightness, so we have to see the both the leading hook straightness and so leading hook straightness and trailing hook straightening factor. So, that we can get. So, case 3, the leading hook straightening during drafting, and here you can see the during drafting the leading hook gets straightened. That means, the you can see the body part mid part of the body has not reached the accelerating point, but the leading hook has reached and it has got sufficient time r is high. So, complete removal will be there leading hook. Now, rear hook, that is a trailing hook, cannot be fully straightened during drafting, because it has actually it is reaching later, okay, and that means body part is reaching later and terminates when midpoint of the rear hook arrives, okay, at the axillate. So, that means the as this fiber for longer fold of the rear hook, it cannot be completed properly, because the midpoint will reach early. So, and the hook will move along with the body. So, the case in the situation is that leading hook length is more than the trailing hook length is more than the leading hook length. So, leading hook, when leading hook length is smaller, so leading hook will get completely straightened, but rear hook will not get straightened, and time required for the leading hook T1 is L3 by VA minus VB by 2. So, this is the time required for the fore hook, and for rear hook this equation is there T2, and where this L multiplied by 2 eta minus 1, which accounts for the body part and the contribution of the straightness factor, and 2 plus L3 is additional fiber portion affected during drafting. The outer fiber straightening. So, this is the outer fiber straightness. So, output fiber. So, this is also given by this equation. Now, where output fiber eta dash is affected by initial fiber straightness, that is always there, this factor will be there, and the draft ratio and the length of the leading hook. So, here length of the leading hook will be there. So, that is why output fiber straightness here, and drafting improves the straightness while longer fore hooks are reduced. So, that is why. Case D, where both fore and rear hook are fully straightened during drafting. So, this is the ideal case here. Now, we can see this is the case D. So, both the hooks are removed. First, there will be removal of the leading hook, and then at the trailing hook. Here we can see interestingly the R value is sufficiently longer. Now, here at T2 portion, the midpoint of the hook, leading hook has reached at the accelerating point. So, it starts straightening and there is a sufficient length is there, R is, so it will take some time to fully straighten, and during that time, after straightening, the midpoint of the body part will reach. So, midpoint of the body part has reached, but at that time the midpoint of the trailing part has not reached, it is under the speed of the back roller. So, this 3 stages. So, first the leading hook is removed, then the midpoint of the body has reached to the accelerating zone. So, first leading hook is getting speed of the front roller, by that time the midpoint and the trailing hook was moving at the back roller speed. Then in the next sequence midpoint has of the body has reached. Now, midpoint along with the straightened leading part is moving at the front roller speed. During that time the trailing part was moving at the speed of the back roller, and during that trailing hook has also reduced straightened. So, the sequential operation is taking place, and which depends on the length of hook L3 L1 and the distance between the nip point of the front roller B and C, the accelerating R. So, that relationship is important here. Time for straightening, you can see the for 4 hooks. So, L3 by V A minus V B by 2, that is 2 L3 divided by V A minus V B, and rear hooks 2 L1 minus V A by V B. So, they are independently acting, and therefore, the time required depends on the hook length and the speed difference. So, that is a hook length is important here. the shorter hook length will have more chance have more time. So, for reaching to the nip point. So, outer fiber straightness eta dash will be 1 if the fibers are completely straightened. Now, case E. So, here we have discussed the both fibers are completely straightened, fully straightened. So, eta dash will be 1 in this situation. Now, case E is that rear hook is completely removed, but fore hook is not removed. Now, here the same situation is there. So, time taken for the straightening of the rear hook, we can see here, this is the relationship where L1 is the length of the rear hook. So, L1 2 L1 minus V A minus V B. So, output fiber straightness, so can be is given by this eta dash equal to L eta plus L1 by L, where L1 is the length of the rear hook plus this component E minus 1, E is the draft, multiplied by 2 R minus L divided by 2 E plus 1 multiplied by L. So, L by L1. So, L1 by L represents the contribution of rear hook to the overall fiber straightness. So, L1 is the rear hook, and this component, the second part is this represents the effect of drafting and front roller. So, that is the R is the distance, the front roller distance, and draft, E is the draft. So, that will affect the straightening. Case F is that the straightening process of the rear hook terminates. So, straightening process of the rear hook when the fore end of the rear hook enters at the front roller nip. That means, if the hook length of the hook is very high, L1 is very high rear end, and the tip of the hook has reached to the front roller nip before it gets straightened. That means, both the body and the tip of the rear hook will move at the same speed of the front roller. Time taken for straightening the rear hook is given by this relationship, where this 2 L multiplied by 2 eta minus 1, the first part, this is the first part and this one is the second part. So, this accounts for initial configuration before drafting, and L by 3, L3 by 2, since the fore hook is partially straightened first. So, this will be partially straightened, and this term accounts for the remaining effect of the fore hook on the fiber overall geometry. So, this fore hook is also not straightened properly. So, average fore hook length is there, it is averaged out. R accounts for the front roller effect. So, this is the R. So, if the front roller pressure is very high, top roller pressure is very high. So, in that case R may be increased. So, this is the front roller effect. The entire expression is divided by V B since. So, this is the entire expression is divided by V B, the back roller speed, because the rear hook straightening process primarily depend on the back roller movement, it considers the amount of stretching time T, the output fiber straightness after drafting can be obtained by this relationship. So, this relationship can be derived where eta is the initial straightening and the first part, this component represents the primary drafting condition, and the other part, the next component E minus 1 square multiplied by 2 r minus L 3 divided by 2 E plus 1 multiplied by L, it considers the higher order drafting force. So, this is the drafting force. Now, case G where R is less than half of the leading hook distance. Okay. You can see here now here this R is less than the half of this distance. That means, what does it mean? Before the leading hook reaches the accelerating point, that means leading hook is not moving at the front load speed. Before that, the tip of the leading hook is reached. Okay, that is leading end of the leading hook is reached. That means, there is no chance of the leading hook getting straightened. So, it will be as it is, this fibers will be, the leading hook will move, that is R is less than L by 3. The straightening process of the rear hook begins when the fore end of the fiber is held by the front roller, while the midpoint of the fore hook is not reached the accelerating point. So, in that case what will happen? In this case the fore hook cannot be straightened. Okay. So, that cannot be straightened here. So, case G, the straightening portion in this same, the straightening process of the rear hook terminates when the fore end of the rear hook is held by the front roller nip. So, here at this point, whatever the rear hook it is actually, it is also in the case of rear hook also, before it reaches the midpoint is reached in the in the accelerating point, the fore tip of the rear hook has reached the front roller nip. So, it is also again the rear hook will also not be removed. So, both the leading hook and trailing hook will remain as it is, they will move as the both end hooks. Time taken for straightening is given by this relationship, which is almost 0, there is no straightening. So, this is the time taken. So, at this point here L 2 eta minus 1 is the for the effect of initial fiber configuration, L 3 is added because the presence of the fore hook adds additional curvature to be removed during drafting. The rear hook straightening process only depends on the back roller speed, thus only VB is considered. So, output fiber straightness is given by this relationship here, where output fiber straightness depend on the initial straightness, draft ratio and fiber configuration. length of the leading hook, length of the fibre, that is total length of the fibre, and case H is the rear hook is completely removed during the drafting process. So, here this is the process. Here we can see the at T3 point, T3 the midpoint, before the midpoint reaches, the leading part is under the grip of the front roller. So, it will be pulled total along with the leading hook, the total fibers will be pulled and will move at the front roller speed, but the trailing part the midpoint is far away from the midpoint of the trailing hook is far away from the accelerating point. So, it will have sufficient time to get removed, to get straightened. The time for straightening of rear hook is this given by L1 by the average speed, the average difference in speed V A minus V B by 2. So, output fiber straightness is given by eta plus L1 by L, where L1 is the length of the rear hook. So, represent L1 by L represents the contribution of rear hook to overall fiber straightness. Eta represents the fiber straightness before drafting. Now, we will discuss the straightening of the clumped fiber. So, we have discussed the straightening conditions of the both end hook fiber. Now, the straightening process of the clumped fiber. A clumped fiber consists of leading and trailing hooks combined in the hook portion. Okay. So, this is the leading and trailing hooks in the. So, there is a this is leading and then it will be trailing. So, this is the clumped fiber. But they are connected, it is not that straightforward, it is a mix, it is not the mixture of leading and trailing hook. So, clump fiber behaves differently from the single hook fibers and has two step straightening process. So, two stages are first straightening process of partial hook removal, then in the second stage complete hook removal. In most of the case it is there. Now, time required T, time for first straightening, partial straightening, then T2 is the second stage straightening, that is the complete straightening. So, case A, hook not completely removed, the clumped fiber remain partially hooked even after drafting. This is the clumped fibers configuration, and we can see after drafting the clumped fiber hook is not completely removed. It might have the it is reduced, but it has not completely removed. Straightening time for fast straightening, this is the for fast straightening T1 equal to 2 L3, where L3 is the length, this length here, and 2 divided by V A plus 3 V B. We can see here we have L1, L2, L3, L4. Now, L1 is this one, L2 is on the other side, L3 is the T1 is here. So, that way it is L3 is the length of the forehook which is straightened fast. So, L3 is the length of the forehook, this is the length, and this is the length of the forehook, and the denominator V a plus 3 b represent the velocity difference governing the straightening process. Straightening time for the second stage, this is the straightening time here, which is actually the second stage straightening time phase is it consists the remaining part of the fiber still needs straightening after the first phase, the partial phase. The equation above accounts for both the initial fiber structure and that is a eta and the influence of drafting parameters, that is E is the drafting parameter. So, we can see here that was T2, T2 here this L3 3 eta minus 1 accounts for the straightening of the fibers body and remaining hook portion. Okay. That is the time this L3 3 this one L multiplied by 3 eta minus 1 and this part second part is a correction factor that accounts for how much the forehook, that is leading hook, contributes the fibers overall straightening during drafting. That is L3 and minus 2 L3, this factor comes because its subtraction is there, the term that ensure the straightening effect of the leading hook is not counted twice. So, it is because the output fiber straightness is given by this equation here, and where the first part, it is a complex equation derived, it captures the primary effect of drafting on the straightness, which by incorporating the fibers original shape, draft ratio and hook influence. So, here you can see the draft ratio, original shape eta and hook influence. So, L3 is the L3 by 2 this part, and the second term which its fine tune of the final straightness value by incorporating higher order effect. So, we are actually here trying to incorporate higher order effect of drafting and fiber length. So, this is for fine tuning of fiber straightness. So, this has been derived. Case B and C, hook is removed in the first stage. So, in the first stage the hook is removed, the hook gets completely straightened in the first stage. So, here we can see. So, during the drafting the hook is completely removed. How? This is the midpoint of the leading part, leading body is reached at the accelerating point. So, it moves at the speed of the front roller, and remaining part, that is moving at the back roller speed. So, it gets straightened, and case C is the, you can see the straightening time here is given by this relationship, and at T0, T2 equal to 0, in case D and E hook is removed in the second stage. You can see when it is reaching at this point, so hook is removed, complete removal is there between D and E. So, first straightening is partial straightening of the hook. So, here there will be partial straightening, and then at the second straightening is the complete process, complete straightening. Now, straightening time is given by this relationship as we have already seen, T 1 and T 2 is given by this equation. So, this part, this component is calculates the total time related which is total time needed for the fiber to reach full straightness in the second stage, and T 1 we subtract T 1 to ensure that we only consider the extra time required after the first stage is completed. So, case B and E, in these cases the fiber velocity changes when the fiber's fore end is nipped by the front roller, and case C and D fiber velocity changes when the fiber's midpoint reaches the accelerating point. Now, in these cases where the front roller affect the straightening, so R is less than L 3 by 2. So, we can see here. So, in that case when the R is very low, so the straightening process starts ahead of time. Okay. The fore end of the fiber is nipped by before the midpoint L 3 is reached at the accelerating point. Case F and G, hook fiber straightened during drafting. Case F is that hook straightening in the first straightening process. So, you can see the hooked fibers are straightened. So, output straightness is 1 because it is completely straightened. Time for straightening the hook is given by this relationship 1 minus eta multiplied by L divided by V A minus V B. So, that can be calculated, and T 2 is 0 because it has already been processed at the first stage. Case G, hook is straightened in the second phase. So, here at the second phase the hook is straightened, and in earlier what we have seen, hook is straightened at the first stage. So, second phase timing we should calculate. So, output straightness is 1, time for straightening the hook. So, T 1 is given by this relationship 4 L minus 2 R plus 1 minus eta L divided by V A plus 3 V B, and this part 4 L 3 minus plus minus 4 R represent the effect of the hook's initial position and distance it travels, and the second part 1 minus eta L represents the portion of the fiber that is still hooked before straightening, and the denominator represents the the rate at which the fiber straightening takes place. So, that is the total time. So, T 2 is given by this relationship. So, the 1 minus eta L divided by V A by V B first term represents the total time required for complete straightening, and however, since the some straightening is already occurred in the first process T 1. So, we subtract that, the total time required T 2 will be given by this. So, T 2 will T 1 will be subtracted. Now, case H, this is the case H where first drafting process terminates when the fore end of the hook enters in the front roller. So, this is the fore end of the front, the hook portion, fore end of the hook enters into the nip of the front roller. So, that first drafting will terminate here, it will automatically move. So, the fibre then move at the speed of the front roller. So, fibre will start moving at the speed of the front roller. Time taken for straightening the leading hooks will be L 3 by V b, V b is the speed of the back roller and L 3 is the time length. So, since the hook straightening process occurs before the fibre reaches the front roller, the only factor affecting the time is how fast the fibre is moving at the speed of the back roller. So, V b is there. Okay. So, T 2 will be 0. So, output fibre straightness is given by this relationship here, where eta represents the original straightness and we are adding some component. This additional straightness which will depend on, so if we increase the draft E, so that will increase the straightness. Okay. And also depends on the L 3, if it is increasing, then straightness will increase, and fibre length, total fibre length. Case 1 said case I and case J is the first straightening process terminates at the time when the midpoint of the hook arrives at the first acceleration point. Now, we can see the midpoint of the hook is arrived at the accelerating point. So, here midpoint of the hook is accelerating. So, that means the first straightening process terminated, because this part hook and the fibre part will move at the speed, at that speed. Time taken for the first straightening process is given by this derivation, this relationship, where it is seen that it is the same as the G, condition G, and case I is the second drafting process terminates when the midpoint L 2 arrives at the fibre accelerating point. So, this is the thing when the midpoint of L 2, this L 2, it actually before it arrives, before this midpoint arrives, the second drafting process terminates. So, time taken for second straightening process is given by this complex relationship, where eta is the fibre straightness, initial straightness, which is less time required for T 2. If it is higher, eta is higher, that means higher eta, more straightness. So, longer fore end hook L 3, more time required. Output fibre straightness is given by this relationship, the input fibre straightness by the term 1 and plus by the term 2. These are the complex relationship which are derived So, term 1 accounts for the primary drafting effect, linear correlation here, and here it is a quadratic correlation. So, terms higher order drafting effect, non-linear correlation. So, this is the drafting correlation, we can derive linear correlation as well as the non-linear correlation. So, here draft is actually power is 1, here it is a square. So, case J, second drafting process terminates when the leading end of the hook enters into the front roller. So, here you can see when the leading end enters here, that means second drafting process will terminate. So, that it will take the hook portion along with the leading end, leading portion. Time taken for second straightening process is given by this relationship, complex relationship that we have already seen earlier. So, this type of relationship can be derived, where this first part, this part represents the initial contribution of fiber geometry and the acceleration distance, and this part is derived which incorporates the drafting effect. So, all these derivations are given in one of the research paper published in Textile Research Journal. One can always go through this, and this denominator part, it is a time required for straightening is inversely proportional to the combined velocities of the draft. So, that is what it is. So, combined velocity. So, fiber output straightening is that this is the output fiber straightness. So, this is a very complex equation where eta represents the initial fiber straightness. So, first component of this accounts for the straightening effect due to draft, and second is represents the additional contribution of fiber movement and draft, and third is it is a higher order that incorporates the second order effect of drafting on straightness. So, we have seen that we can approach the fiber straightening, that is a hook fiber hook removal, by all these different assumptions, and we can simplify if we want, but this discussion is just to give some light how to approach this. We have not discussed here the detailed derivation of this relationship, because our idea is not to derive all this which has already been published, but here what we are trying to discuss is that what is the approach. So, if we take the approach in simpler manner by eliminating some or assuming some other things, that can be simplified, or if we can take some standard value, so that we can derive the straightness at different conditions as we have discussed. Okay. So, we will stop here, and we have now come close to the drawframe section. So, in next section we will start the next process, which is combing. Till then, thank you.